Hi, and we are still angular displacement, and we also talked about arc distance. And in this lesson, we are going to look at angular velocity. Angular velocity. I have this circle. This as the center. We have a point A. We have a point B. I'll draw a line to join the point A and the center, and the line to join B to the center, and I'm going to call this angle the angular displacement. Angular velocity, that is what we are looking at. Angular velocity. I'm using the symbol, and we call this symbol omega. We call this symbol omega. It looks like W, but it is not. Look at it carefully. Omega. And that is what we are using to represent the quantity angular velocity. Now, if I take the angular displacement and I divide it by the time t, then this ratio is what we call the angular velocity. The angular velocity. And therefore, we define angular velocity as the ratio of angular displacement to the time taken. Or we define angular velocity as the rate of change of angular displacement with time. The rate of change of angular displacement with time. That is angular velocity for you. Now, looking at the mathematical expression for angular velocity, we want to look at the SI unit. You remember we said angular displacement has the SI unit as radian. So I'm going to write the units as they appear in their mathematical expression or the equation. And I will divide it by the unit of time, which is seconds. And when you simplify this, it is simply written this way: radian per second. Or you can write it this way: radian per second. So this is the SI unit of angular velocity. But you know what? We can have other units. Other units for angular velocity. Other units. And these other units, one of them is revolution per second. Revolution per second. We should find a way to change from revolution per second to radian per second, because that is the SI unit. And I've said it before that when you are working question in physics, if possible, change all the units to SI unit. It's always proper and convenient to do that. So a question has been given to you, only for you to find the angular velocity expressed in revolution per second. There should be a way to convert it to radian per second. So let's look at it. Now, this revolution, if I go one revolution, as you can see from here, one revolution, right, means I'm just going step by step. One revolution means you have gone through a total angle of 360. Can you see that? So it means that one revolution per second is 360 degrees per second, step by step. But we are lucky to know that 360 degrees is equal to 2 pi radians. This 360 is 2 pi radians. What does it mean? It means that one revolution is also equal to 2 pi radians. I hope you are fine. Watch this. I just took this unit and I want to see what that revolution means. Oh, when you go one revolution, it means that you started from a point A and you've gone around the circle back to the point A again. And that is one revolution. And that one revolution has an angle of 360. So I'm just going by that. So one revolution is 360. That will take the place of this. And I'll bring per second again. Then I ask myself, this 360 degrees, do I know it's equivalent in radians? Yes, I do. And we know it here, that 360 degrees is 2 pi radians. So it means that one revolution is also 2 pi radians. Hence, one revolution per second is the same as 2 pi radians per second. As simple as that. So let's see, if for instance you have been given that a body moving along a circle performing circular motion has an angular velocity of 0.8 revolution per second. How do you convert this? How do you convert this one into radians per second? Then we just look at this expression. Watch this one. This is what we are going to do. If one revolution per second is equal to 2 pi radians per second, then therefore 0.8 revolution per second, what to be is equivalent in radian per second, and that will be 0.8 divided by 1, as you can see from here, times 2 pi, and the answer you get here will be radian per second. And you can put the value of pi as 3.142 into this, and you just evaluate it, and that will be in radians per second. So take note of this. Then this angular velocity we are talking about can appear in three different forms. One of them is angular velocity called uniform angular velocity. Uniform angular velocity. What is this? We are talking about types or forms of angular velocity. The first one to look at is uniform angular velocity. What is it? Already we have met this word uniform, and I want to repeat it. Anytime you are dealing with motion, a body in motion, and you happen to see the word uniform, it simply means constant. This word uniform simply means constant. All right, so what we are going to do is that we are going to cover the uniform, define angular velocity, and we shall add the uniform to it. So watch how I'm going to do it. So simple. They want us to explain or define uniform angular velocity. So I'll go. It means I'm going to cover this. What is this? Angular velocity, this one, is defined as the rate of change of angular displacement with time. That alone will take care of this. Then I will take my hand off and I will say that it is the rate of change of angular displacement with time being constant. You see how simple it is? So uniform angular velocity is defined as when the rate of change of angular displacement is constant. It means that it is not constant. It is not constant. All right. So I'm going to close my eyes on this non-uniform and look at the definition for angular velocity. Then I will add this one to it. All right. So let's go. A body is said to have a non-uniform angular velocity if the rate of change of angular displacement with time is not constant. Is not constant. That is it. But you see, having defined the two, I'm going to give you another way by which you can also define this uniform and non-uniform. And I'm going to do that using this diagram. And I want you to watch this carefully. I have this circle. And I have a body moving from a point A through to B, C, D. The body is moving from A to D. And in fact, the body does not stop at B. It doesn't stop at C. It is moving from A through B, C to the point D. And we check. And when we check, between A and B, it has gone through an angular displacement of, let's say, 30 degrees. From B to C, it has gone through an angular displacement of 30 degrees. And here to the same angular displacement of 30 degrees. Watch this carefully. A body is going along this circle from A through B, C, and finally get to D. And between A and B, it has gone through an angular displacement of 30 degrees. Between B and C, an angular displacement of 30 degrees, and C to D, an angular displacement of 30 degrees. What it means is that the angular displacement is the same between any two successive points. Any two successive points, the angular displacement is the same. Now let us assume, listen to me, let us assume that when we change this 30 degrees into radians, we are getting, I'm just assuming it for the sake of us going through easily. Let us assume that this angular displacement of 30 degrees is 4 radians. 4 radians. So this is also 4 radians. This is also 4 radians. All right. And it has taken a time of 2 seconds from here to there, from A to B, and from B to C the same 2 seconds, and from D to C to D the same 2 seconds. Okay. Can we find the angular velocity here? We can do that. So the angular velocity between A and B. So angular velocity between A and B is simply the angular displacement, which is 4 radians, divided by time, which is 2 seconds. And we are getting 2 radian per second. What about between B and C? So the angular between B and C, the angular velocity is the angular displacement divided by time. And we are getting the same 2 radian per second. When we divide 4 radian by 2 seconds, this is what we are getting. And then between C and D, we are also getting the angular velocity to be 2 radians per second. It's not constant. It is not changing. So the angular velocity is constant. But we got it to be constant because, watch it, the body covers equal angular displacement using equal times. I hope you are checking my finger. The body is having a constant angular velocity because the body is covering equal angular displacements using equal times. And therefore one can say that a body is also said to have a uniform angular velocity if the body moves through equal angular displacement using equal times. Anything short of this will make it non-uniform. Anything short of this will make it non-uniform. And therefore we can say a body is said to have a non-uniform angular velocity if the body covers equal angular displacement using different times, or we cover different angular displacement using equal times. That is another way by which we can define uniform angular velocity and non-uniform angular velocity. The next type of angular velocity is instantaneous angular velocity. Instantaneous angular velocity. What is it? It means that we are looking at the angular velocity at a particular instant. From the word instantaneous, we can say that we are looking at the angular velocity at a particular instant. This is what it means. I have a body going along a circle. Now, somebody stands at this point here. Somebody is there with an instrument to measure the angular velocity. Now, the moment the body gets to this point, that person switches on the machine to record the angular velocity at this particular instant, at this particular moment. Now, that value is what we call the instantaneous angular velocity. But let's look at the definition. Again, I'm going to cover this. I'm going to cover instantaneous and first define this one, and then we shall continue to add something to it. And therefore, the instantaneous angular velocity is defined as the rate of change of angular displacement with time at a particular instant in the course of the motion. In the course of the motion. The fourth type of angular velocity is the average angular velocity. Now, as far as motion is concerned, anytime you meet the word average, it is talking about total. You meet the word average in motion, it is talking about total. Now watch this. I'm going to close my eyes on this. I'm going to close my eyes. Let me first erase it. So you know that you see the expression or the definition for average angular velocity. We are only going to define angular velocity. and that is defined as angular displacement divided by time. This is the definition. This is the definition for angular velocity. It is defined mathematically as angular displacement divided by time. The moment I put average here, oh, as I said, we are talking about time. Sorry, we are talking about total. And therefore, I'm going to put total here, down here, and I'll put total at the top here. And that is all. So, the average angular velocity is radian per second. Bye.